When Dolores asked me to give a talk, normally I like to give talks that have to do with research, or at least, stuff I have been thinking about in, the last few months or the last couple of years. And this is stuff I have been doing, which is still not published. It's equal weights and weighting against homoplasy, and when do they produce identical trees. This stuff is not published, but in a chapter on character weighting in a book of mine on phylogenetics that's coming out next July, this subject is being discussed, but it is still not published. Now, character weighting is still a controversial subject and poorly understood by many. Some researchers are completely opposed to any form of weighting, while others consider it wholly natural and logical. And I suppose most of you must know that I am one of those people who consider it natural, because I have done a lot of work on character weighting. Now, the main argument I want to develop in this presentation is that both sides of the controversy, the ones who are both pro and against character weighting, may have points of contact, in that we can expect differential and equal weighting to produce similar results in specific circumstances. But if those circumstances are unlikely to arise in empirical analysis, then despite the points of contact between both positions, thinking about weights is still necessary. Now, before we enter into details, I have to do some history and generalities about weighting. Obviously, when two or more characters conflict, that is, they determine incompatible groups, at the most, one of the characters can be right. Maybe both characters are wrong, but it is impossible for both characters to be right at the same time. If we can trust some of the characters more than the others, then we have a good reason to resolve that conflict in favor of the more reliable characters, obviously. Since the 80s, there is a widespread belief that parsimony requires that all characters be assigned the same weight. So people tend to think that if you do character weighting, you are not doing parsimony. So a number of authors have expressed that opinion. For example, Rippel, in his book in 1988, said that to recognize a character is to recognize a group. Weighting of characters, therefore, cannot proceed independently of a hypothesis of grouping and hence of relationship. Or to put it in other words, characters weight themselves. And he said this paraphrasing Patterson, 1982, another influential paper. This meant forget about differential weighting. Patterson's argument, on which Rippel was borrowing, was that if you recognize true synapomorphisms, then you do not need to weight synapomorphisms. They will all be congruent, they will form a perfectly hierarchical pattern. So Patterson said, on weighting, it is argued that the systematist has no role to play. Homologies weight themselves. Hold on one second, I have a WhatsApp. Maybe they're telling me that I'm gone. No, something else. Okay. That is true as far as it goes, but how on earth are you going to recognize the truthfulness of an apparent synapomorphy? If you have two characters in conflict, only one of them can be true. So you really still need to solve that problem. Some evolutionary systematists express the opinion that you can lower the weight of characters that are more adaptive or less adaptive. For example, Eldridge and Cracraft, in his influential book of the 1980, criticized this viewpoint. And they say that we merely reiterate the fundamental observation that all characters are evolutionary novelties, that is, synapomorphics at some level. The problem is to find that level for each character and not to assume that some features are better than others, basically. So for these authors, the conclusion was simple. We do not know how to find out which characters are more reliable. Therefore, all characters must be given the same weight. Note that this is an argument that stems from ignorance. It does not rest on the idea that the characters are in themselves really equally reliable. Even phoneticists recognize that there can be better and worse characters, but used equal weighting only to bypass their inability to determine which characters are better or worse. Then in the mid-90s entered Arnold Kluge with the right-chose phylogenetics, and he was a really strong proponent of equal weights. And he cited Farris 1983 in support of his views, at least initially. For example, in this paper, he said, in cladistics, the least refuted hypothesis is the most parsimonious cladogram in his mind that was only equal weights that minimizes requirements for ad hoc hypothesis of homoplasy. Some people cited Kluge, and they continued citing Farris, like Miller and Ormiga, who said that since the minimization of ad hoc hypothesis is critical to the relationship between evidence and science, defense of a hypothesis requiring more than the minimum number of character state changes to explain observations must be accompanied by a compelling argument for why the parsimony criterion should be relaxed or justified by something other than parsimony. Then Grant and Kluge also were very vocal in their opposition to differential character weighting. For example, they said that equal weighting maximizes character congruence over all data, and it is the only assumption set that does not violate the tenets of objective ideographic inference. Similar anxiety over weighting has been expressed in languages other than English, for example, by Williams and Ebach, 2007, in their book. I'm not sure I fully understand the language here, but I can see that they are concerned with weighting schemes. They are against different forms of weighting. Now, many people have cited Farris for the idea that parsimony equals equal weights. Is that correct? Let's see what Farris himself said in terms of weighting. He said, no one supposes that characters in general all deserve the same weight, that they all yield equally strong evidence. Drawing conclusions despite conflicting evidence requires that some evidence be dismissed as homoplasy. It is surely preferable to dismiss weaker evidence in deference to the stronger. A decision reached by weighting characters at any rate can hardly rest on a basis different from parsimony. So it's clear that for Farris, equal weights your mama. So that leaves us with the problem of how do you identify more and less reliable characters? Okay, you need to do that still. Well before cladistics, evolutionary taxonomists had the idea that more homoplastic characters need to be considered as less reliable. They thought that one could use notions of whether a character is adaptive or not as an argument for determining its weight. This is highly problematic. You can make, for example, the argument that the character which is adaptive should be given lower weight, and that may be reasonable. But you can also make the argument that the character which is adaptive should be given a higher weight. So you cannot really use degree of adaptation for weighting characters. Homoplasy is just the manifestation of unreliability. The character that is uniquely associated with the group is perfect for recognizing the group. It's error-free. A character that changes in many parts of the tree will allow recognizing some groups, but just following the dictates of the character by itself would lead to an incorrect tree. The more homoplasy, the more incorrect the tree. So using homoplasy to infer reliability is wholly agnostic in terms of the causes of the unreliability itself, whether it's adaptiveness, lack of adaptiveness, or whatever. The problem here is on which tree you should measure the homoplasy, because for any character, some trees have homoplasy and some trees don't. The first practical approach to cut this Gordian knot was by Farris with successive weighting. Sorry, I'm getting WhatsApps and I need to know. Okay. I'm afraid that I might be getting a WhatsApp to letting me know that the communication was cut. That's not the case. Otherwise, I will be silencing my cell phone, but I can't. In successive weighting, the homoplasy is measured on the best trees found so far, then used to calculate new sets of weights and produce a new inference. The hope is that the estimation will gradually converge onto the right weights. In 1993, I proposed a method derived from successive weighting, which I call implied weights. Implied weights refine successive weighting, eliminating the dependence from a starting point and incorporating the weighting criterion into the measure of optimality itself. And it's the method for weighting parsimony used most commonly today. The method is based on scoring trees with a function where the cost of every additional step is less and less. In that way, characters that have more homoplacy on the trees being compared, for example, optimal and near optimal trees, are less influential. Like equal weights parsimony, implied weight assumes that the probability of change for the characters is not concentrated on certain branches of the tree, thus differing from the standard MK model normally used in maximum likelihood. That is, parsimony can be justified as a likelihood method when all branches of the tree have the same probability of change. Now we can finally move on to the question for this talk: when do equal and implied weighting produce similar results? An obvious and trivial answer: when all characters have the same homoplacy, which is to say, the same reliability. But the problem is more interesting than just that. There are two recent papers that present findings which bear on this problem, and this is also discussed in my forthcoming book. The first paper is by Goloboff and Wilkinson, 2019, who show that for any given tree T, if you select all the possible character state distributions that have a given number S of steps on that tree, and you analyze the resulting matrix, either with likelihood or parsimony, you get the exact same tree T, as long as the number of steps S is within a fourth of the number of taxa. The same is true if instead of getting every possible character distribution with the S steps, you get a large enough sample of the characters that have S steps on tree T. With this, you can generate, for example, a matrix for 1,000 taxa and say 3,000 to 4,000 characters, each of which has 250 steps on tree T. If you analyze that matrix with parsimony, you produce the same tree T, even if every character has 250 steps. Obviously, the analysis of such a matrix with equal or implied weights is going to produce exactly the same results. On tree T, all of the characters have the same homoplacy. The cases illustrated by Goloboff and Wilkinson do not have a model tree in the sense that a model is understood in statistical phylogenetics today. Goloboff and Arias in 2019 also report a similar phenomenon for datasets generated in the more standard fashion. In parsimony, character changes are assumed to occur equiprobably on all the branches of the tree. So in a Poisson model, like the one normally used in maximum likelihood analysis, you can do this by setting the length of all the branches of the tree to the same value. So we generated in 2019 data sets with such a model using the same branch length for all characters. So this amounts to equal weights parsimony. All characters have the same probability of homoplacy. And we found that for large numbers of characters, the tree that maximizes the likelihood is identical to the parsimony tree and identical to the model tree, even when the branches are very long, which is to say, when there is a lot of homoplacy in all of the characters. This situation resembles the one I have studied together with Wilkinson. Large numbers of equally reliable characters produce the right tree, even when character reliability is very low. Now, this raises an interesting question, and this is the crux of this talk. If a matrix formed by many characters of the same reliability, R1, produces the correct tree, and so do matrices formed by characters with reliability R2 and R3, 4, all the way to N, then the matrix formed by combining characters with R1, 2, 3, all the way to N should also produce the same tree. Every matrix individually gives the same tree, they all combined give the same tree. Which is to say, characters weigh themselves. There is no need to sort out good and bad characters. Parsimony does this by itself, which is more or less what conventional wisdom expected, like Patterson, Eldridge, and Crackraft in the 80s Klugian, Grant, etc. For example, Wenzel and Sidal in this quotation are also skeptical of differential weighting. This just follows from the fact that if enough characters are included in the matrix, a matrix with all the characters of equal reliability will produce the correct tree. However low the reliability of an individual character is. No further analysis are needed for this conclusion. It is only a matter of logic. Note that homoplacy weighting still produces the same result as equally weighted parsimony. The results are identical and there is no harm in differentially weighting against homoplastic characters. But does this not render character weighting wholly unnecessary? Yes, it does, but only when the number of characters is very, very large. If only a few characters of each type are included in the matrix, then the situation is very different. When there are few characters of equal reliability, the matrix rarely produces the correct tree. If the individual matrices of reliabilities are 1, 2, 3, all the way to n, each produce different trees, then it makes sense to pay less attention to those matrices, which is to say characters, that have a lower reliability. In this connection, weighting against homoplacy will make those characters, which are more likely to mislead, less influential. Thus, weighting can be expected to make a difference for lower numbers of characters, which is what you can expect for morphological data sets. This is just logical reason, but it can also be tested with simulations, which are so fashionable today and help test the correctness of my reasoning. Any simulation needs, of course, to assume some model of evolution. I did simulations with the Poisson model where all the branches of the tree have the same length, but differing among characters so that there are more and less reliable characters. The model tree is a random tree, and I measure the distance to the model for trees inferred using equal weights and implied weighting. The data sets have 100 taxa and from 20 to 1500 characters, and I tried 14 different numbers of characters, slightly increasing the number of characters. For each number of characters, I simulated 96 data sets, which is to say like 100, but 96 is a perfect multiple of the number of processors I was using in my parallel calculations. That's why you have that strange number. And I analyzed each data set with one random addition sequence plus TBR branch swapping, plus a random sectorial search, plus 5 iterations of ratchet. And I removed and supported rules. I did 20 different combinations of branch lengths and branch length spreads. And this is about 90,000 simulated data sets or 180,000 analyses because I ran equal and implied weights. Here we have some results. For example, the first tile in the upper left side of the diagram is showing you on the x-axis the number of characters increasing from 20 to 1500. On each diagram, you have the minimum and maximum branch lengths. Therefore, in this case, for example, all the characters have the same branch lengths or reliabilities. As an inset, you have the homoplacy distribution in each diagram. This means that the peak of homoplacy is at 0 steps in here. And I measure the distance to the model tree with the retention index at circles and the Robinson-Fowles distance. The pink and the white are implied weighting, and the darker colors, red and black, are equal weights, okay? And for the Robinson-Fowles distance, the dots that are closer to the bottom axis are closer to the model tree. And for the retention index, the points that are closer to the top axis are closer to the model tree. So if you look at the different diagrams, as you go towards the bottom of the screen, you increase the spread, you increase the difference between minimum and maximum branch length, which is to say you increase the differences in reliability in the characters of the matrix. And as you move to the right of the diagram, you increase the length of the shortest branch, which is to say you decrease the reliability of those of the most reliable characters, or increase the overall homoplacy of the matrix. So this is a summary of what happens as you move in the different sub-diagrams in here. You can see that when there are small differences in homoplacy in the characters, there is no harm in doing implied weight, because in that case, all characters are equally or almost equally reliable. But as differences in reliability increase, then implied weights outperforms equal weights more strongly, and for medium numbers of characters. If we look at the bottom part of the diagram, we will see that, as expected, for example, in here, both equal and implied weights converge to the correct tree and converge to the same result as you have very large numbers of characters. Remember that this is 1,500 characters, but when you have 500, or this would be like 1,000, and this would be like about 500 characters in here, there are clear differences in favor of implied weighting. Vertical bars show the standard deviation, and remember that every one of these dots in here represents about 100 different data sets. Of course, there is variation, and because there is overlap between the standard deviations, you can have an individual data set where equal weights produces a better result than implied weights, but clearly that is not the norm, okay? So as you have medium numbers of characters, even if there is a lot of variation, implied weights clearly is implied weights is clearly outperforming equal weights in here. Now, this is, of course, a specific model. There is no guarantee that in the real world equal and implied weighting are going to behave like this, but it is better than nothing and suggests that the logical reasoning I had done before is correct. In 2018, we also found that different partitions of empirical morphological data sets do not share branch lengths as is expected in the MK model, but they do not have either as much heterogeneity as expected for the model which I just used. That model is a model where a character can equally well change anywhere in the tree, and there is absolutely no correlation between branch lengths or longer and shorter branch lengths. In that paper, we examined a model for generating data, which we call episodic. This model creates branch length heterogeneity, and that branch length heterogeneity is similar to the one you observe in empirical morphological data sets. This model assumes that characters can change in only parts of the tree, but where they can change, they do not have a higher probability of change in some branches. That is, they do not respond to a common model as in maximum likelihood. This model for simulating data sets was inspired in Farris 1983. In 1983, criticizing maximum likelihood, Farris said that it seems more likely that horseshoe crabs have evolved more slowly than insects, that tooth counts change more frequently in fishes than in mammals, and that paired appendages generally do the opposite. He continued, indeed, the general success of hierarchic summaries of characters of organisms seems to suggest that each feature undergoes evolution in only restricted part of the evolutionary tree. That is, after all, what is implied by the observation that the synapomorphisms of tetrapods involve different traits than do those of hymenopterans. In my view, this continues being one of the strongest arguments against the model assumed by standard maximum likelihood, and is as valid today as it was almost 40 years ago. So the main problem with the uncorrelated model is that characters cannot, in the real world, equally well change anywhere in the tree. Vertebrae cannot change in insects, teeth cannot change in birds. So this may be more reasonable. Within the red zone, all characters change in an uncorrelated way, that is, with the same probability at any red branch. And the characters cannot change at all in the black zone. That would be a group of characters, but different groups of characters can be modifiable in different parts of the tree. So if you put all of these together, you are going to have a tree with different groups of characters of different colors. And on the tree, you are going to have branches where one group of characters can change. you are going to have branches where 2 groups of characters can change and branches where 3 groups of characters can change. So there's going to be shorter and longer branches, even if there is no a common model as assumed in maximum likelihood. In data sets generated with this model, the reliability of a character that can change only in a reduced part of the tree, that is having little homoplasy, perhaps could be assessed incorrectly relative to the reliability of a character that can change over all the tree. Therefore, it makes sense to check to see what happens with implied weights when analyzing data sets generated under such a model. So we generated another 90,000 data sets and did the 180,000 analysis, just like before, and you see exactly the same pattern. When you have significant differences in homoplasy, you have, for medium numbers of characters, implied weights clearly outperforming equal weights. You can see in the homoplasy distribution here, for example, you have the peak of homoplasy at 12 steps, but you still have a significant proportion of characters with no homoplasy. As you increase the overall homoplasy, remember that's to the right, you start having an almost zero probability of characters with no homoplasy in your matrix. These amounts of homoplasy are actually larger than what you observe in empirical data sets. Now, another possible problem with implied weights. Some paleontologists think that the many missing entries in their data sets can be problematic for implied weights because as you eliminate entries from a character, you decrease its homoplasy and therefore increase the weight just because you cannot detect the homoplasy. So in 2014, I proposed a way to take this into account, modifying the weighting function to accommodate missing entries. And in this method, missing entries do not lower the weight by themselves, but the weight for characters with missing entries decreases faster with homoplasy. So I generated data sets, chose 25% of characters at random, and for those chosen characters, I chose 50% of the tags at random for replacement with missing entries. You do another 180,000 analysis, and again, you have exactly the same pattern as before. As you have very, very large numbers of characters, implied and equal weights converge to the same results, but for medium number of characters, implied weights has a substantially better performance in terms of distance to the model tree, either when measured with Robinson-Falls distance, as the curves below, or when measured with the retention index as the curves on top of the diagram. Now, I was stressing that the distribution of homoplasy in those simulated data sets is even, there is even more homoplasy than in empirical data sets. And I wanted to mention that because in a series of papers against implied weighting, O'Reilly et al. And Putig et al., it's the same set of co-authors, just switching the order, have said that the data sets we simulated in a paper we published in 2017 have qualities that strongly bias in favor of parsimony phylogenetic inference and implied weights parsimony in particular, as the presence of large numbers of characters that are congruent with the tree allows implied weights to increase the power of these true congruent characters. And they said, this effect will not be possible when increased levels of homoplasy are present, or when the true tree is unknown, as is the case for all empirical data sets. Well, increased levels of homoplasy, again, your mama, we have just seen that for very large levels of homoplasy, implied weights continues outperforming equal weights. And also, implied weights does not require that the true tree is known. A method for inferring trees that requires that you know what the true tree is would be absurd. If you know what the true tree is, you just go with that tree. This just shows how little they understand implied weights or phylogenetic inference. Now, Putig and O'Reilly et al.'s crusade against weighted parsimony can be criticized from many more points of view, of course, but I do not have the time to go into details here. I'll be happy to do so on the section on questions if anyone wants to ask. But perhaps the only detail worth mentioning here is that in connection to Putic and O'Reilly et al.'s papers is that when designing methods, the probability of getting the right tree, which is what you can explore in simulations, is not the only concern. The internal logic of the methods and whether they make sense in light of what we know, for example, that some characters can be more reliable than others, that seems more important than just getting the right tree. And weighting against homoplaces seems well justified in that regard. So the important message of this talk is, yes, equal weights parsimony makes sense and will probably produce the correct tree, identical to implied weights parsimony when there are many characters. So one does need to concede the point to those authors like Kluge, Grant, Sidal, etc., who believe that equal weights is the only way to go. However, in any real case where only a few hundred characters are available, as in morphological datasets, differential weighting is very important and something you should consider very seriously. With that, I'm going to thank you for your kind attention, and if anyone happens to have any questions, I'll be happy to